Hello everyone, I am Vedang Savarkar, 19 BC 1303, and today we will learn about digital signature algorithm. This is digital assignment 2 under the course Blockchain and Cryptocurrency offered in Vellore Institute of Technology, Chennai by Dr. Ganesan R. Now let us understand what is digital signature. Digital signatures are the public key primitives of message authentication. The objective of digital signature is to authenticate and verify documents and data. It is just like the normal signature that we do on paper on any government documents. The signature tells us that the document has been signed legitimately by a person who knows about it. This is necessary to avoid tampering and digital modification or forgery during the transmission of official documents. In the physical world, it is common to use handwritten signatures on handwritten or typed messages. They are used to bind signatory to the messages. It tells us that the person who has signed the data is the one who is sending the message. Similarly, a digital signature is a technique that binds a person entity to the digital data. This binding can be independently verified by receiver as well as by any third party. Digital signature is a cryptographic value that is calculated from the data and a secret key known only by the signer. In the real world, the receiver of message needs assurance that the message belongs to the sender and he should not be able to repudiate the origination of that message. This requirement is very crucial in business applications since likelihood of a dispute over exchange data is very high. So in case of any business application, if the forgery has been done, then it can cause severe damage, and that is why if we have a digital signature, then we will always be able to know who the sender was. Before diving into digital signature algorithm, let us first learn about asymmetric encryptions. In asymmetric encryption, we use two distinct keys, one for encryption and other for decryption. So we use public key for encryption. The public key and private key are the two keys used for encryption and decryption. The public key is used for encryption and the private key is used for decryption. So in this figure, as we can see, we have an original text which is a document which we need to send to a receiver. But we cannot send this data directly. We need to encrypt it. So for this, we will be using a public key of the receiver to encrypt this data. Now this data has been encrypted. This encrypted data will be sent to the receiver. Now receiver will have to decrypt the data. In order to decrypt the data, the receiver will use his own private key to decrypt the data and get the original text. And this public key and private key are two different keys. And these keys must be generated from the receiver's end, both of these keys. Using separate keys for encryption and decryption has helped eliminate key exchange. As we can see in the figure, sender encrypts the data using public key of the receiver. The encrypted data reaches the receiver and he uses his private key to decrypt the data. This is an example of asymmetric encryption. Let us say there are two people, Alice and Bob. Alice needs to send a message to Bob and she needs to send it secretly. So both the private and public keys of the so both the private and public keys of Bob must be used for encryption and decryption. This eliminates the requirement for sender and recipient to exchange any secret keys, minimizing the window of opportunity for exploitation. So in step 1, Alice uses public key of the Bob to encrypt her message. This encrypted message is then sent to Bob. Now Bob will use his own public key to decrypt the message. In this here, public key and private key were used of Bob. Now that we know how asymmetric encryption works, we will look at how digital signature architecture is set up. The objective of digital signature is to authenticate and verify documents and data. This is necessary to avoid tampering and digital modification or forgery during the transmission of official documents. So, if we sign a document with the digital signature, which is the private key of the sender, it means that the sender himself is the one who is sending the message. In digital signature, the signature is encrypted using the private key and decrypted using public key. The private key belongs to the sender and public key also belongs to the sender. While encryption, private key of the sender is used, and for decryption, public key of the sender is used. Because the keys are linked, decoding it with the public key verifies that the proper private key was used to sign the document, thereby verifying the signature provenance. In this figure, as we can see, we have a message which is a plain text. Then we have a hash function h. Then we, by using this hash function, we encrypt the message to get a hash digest, which is small h. We concatenate the plain text and the digest together, which is represented by this plus symbol. Then we perform encryption on the bundled text using the private key of the sender, which is represented by E. And then we decrypt the sent data using the public key of the sender. Now let us look at some of the steps involved in digital signature algorithm. The original message is first passed to the hash function denoted by h hash to create a digest. So as we can see, this is the original message of plain text M. It is sent to this hash function h hash to generate a message digest which is represented by small h. Next, it bundles the message together with the hash digest h and encrypts it using the sender's private key. So this hash digest small h is concatenated with the original message. It is bundled together. And now we will use the sender's private key to encrypt this bundle or the concatenated message. Now this M and H together concatenated is encrypted using the private key of the sender. It sends the encrypted bundle to the receiver who can decrypt it using the sender's public key. Now the receiver will use the sender's public key to decrypt the message that the sender has sent to him. The sent message is concatenated or in bundled form. Once the receiver decrypts the message, it is passed through the same hash function h hash to generate a similar digest. The receiver receives the bundle or concatenation of message and its hash from the sender. So the message and hash both are available with the receiver. Now to check the validity of the message, the receiver will use the decrypted message and he will send this decrypted message to a hash function and generate a digest. The receiver also has received a hash digest from the sender. Now, the receiver will compare the received hash digest and the generated hash digest at receiver's end, and if they both match, then we can say that the data is verified. Let us look at the digital signature algorithm. Digital signature algorithm is a FIPS, Federal Information Processing Standard for digital signatures. It was proposed in 1991 and globally standardized in 1994 by National Institute of Standards and Technology. It functions on the framework of modular exponentiation and discrete logarithmic problems which are difficult to compute as a brute force system. Let us look at the DSA model. Generally, the key pairs used for encryption or decryption and signing or verifying are different. The private key used for signing is referred to as signature key, and the public key is the verification key. So now from this point of time, we will refer the private key as the signature key and the public key as verification key. Let us look at the steps involved in the DSA model. Step 1 is signer feeds the data to the hash function and generates the hash of the data. Here we can see this is the signer side or the sender side. The signer will have a data and he will use a hashing function to hash the data. Step 2 is hash value and signature key are then fed to the signature algorithm, which produces the digital signature on the given hash. So we can see that the generated hash and the signer's private key are sent to a signature algorithm. It will produce digital signature on the given hash. This signature is appended to the data and then both are sent to the verifier. So we can see that the data, original data and the generated signature are bundled together or concatenated and then sent to the receiver. Step 3 is verifier feeds the digital signature and the verification key, which is the public key, into the verification algorithm. The verification algorithm gives some value as output. So this bundle is sent to the receiver. Now the receiver will use a verification algorithm to verify whether the received message is authentic or not. For this a verification algorithm, the receiver uses signer's public key to generate the hash of the received message. Uh, the receiver also receives the hash function uh, and he uses the hash function to hash the data. And now he will compare the generated hash and the received hash. If they both match, then we can say that the message is verified. Verifier also runs same hash function on received data to generate hash value. For verification, this hash value and output of verification algorithm are compared. Based on the comparison result, verifier decides whether the digital signature is valid or not. Based on the comparison result, verifier decides whether the digital signature is valid or not. Since digital signature is created by a private key of signer and no one else can have this key, the signer cannot repudiate signing the data in the future. This methodology is implemented using DSA algorithm. Instead of signing data directly by a signing algorithm, usually a hash of data is created. Since the hash of data is unique, representation of data is sufficient to sign the hash in the place of data. The most important reason of using hash instead of data directly for signing is efficiency of the scheme. Now let us look mathematically how digital signature algorithm works. Step 1 is key generation. We first choose a prime number q, which is known as the prime divisor. Another prime number p is chosen such that p minus 1 mod q is equal to 0. P is called the prime modulus. Choose an integer g such that 1 is less than g and is less than p, where p was our prime modulus. G will be chosen satisfying two conditions such that g power p mod p is equal to 1 and g is equal to h power p minus 1 by q mod p. X is our private key and it is a random integer such that 0 is less than x is less than q such that x belongs between 0 to q. Y is our public key and we can calculate it as y is equal to g power x mod p, where x is our private key and p is the prime modulus. Now, the private key package generated is consists of the prime modulus p, q, g, and our private key x. The public key package consists of p, which is the prime modulus, q, the prime number, g, and y, which is the public key. Step 2 is signature generation. It passes the original message M through the hash function hash to get our hash digest. It passes the digest as input to a signing function whose purpose is to give two variables as output S and R. S and R are the two output variables generated by the signing function. Apart from the digest, we also use a random integer k such that k lies between 0 and prime number q. To calculate the value of r, we use the formula r is equal to g power k mod p whole mod q. If r is equal to 0, then we select a different random integer k. Now we compute I such that k into I mod q is equal to 1. I is called the modular multiplicative inverse of k modulo q in this case. Then we compute S, which is equal to I times h plus r times x mod q. If S is equal to 0, we select a different integer k. It then packages the signature as R and S. The entire bundle of the message and signature consists of the original message M and the two variables generated by signing function, which are R and S. This bundle is sent to the receiver. Step 3 consists of signature verification. We use the same hash function hash to generate the digest h. Then we pass the digest off to the verification function, which needs another variable as parameter 2. Now we compute the value of w such that S times w mod q is equal to 1. Here w is called modular multiplicative inverse of S modulo q, where S was one of the variables generated by the signing function. Now we calculate the value of u1 from the formula u1 is equal to h times w mod q. We also calculate the value of u2 from the formula u2 is equal to r times w mod q. The final verification component v is calculated as g power u1 into y power u2 mod p whole mod q. This compares the value of v to the value of r received in the bundle. If it matches, the signature verification is complete. Let us have a look at all the advantages of digital signature algorithm. First advantage is that it is highly robust. Digital signature algorithm is highly robust in the security and stability aspect compared to alternative signature verification algorithms. DSA has better speed. The key generation is much faster compared to RSA algorithm. DSA uses less space. DSA requires less storage space to work its entire cycle. DSA is patent-free. When NIST released, it was patent-free to enable its global use free of cost. DSA uses message authentication. We can verify the origin of the sender using the right key combination. Integrity verification. We cannot tamper with the message since it will prevent the bundle from being decrypted altogether. DSA uses non-repudiation. The sender cannot claim that they never sent the message if verifies the signature. So these were the advantages of digital signature algorithm. This was all about digital signature algorithm. Thank you.